Welcome to NOAA Central Library's online platform for the presentation of research and ideas in support of the National Oceanic and Atmospheric Administration's mission. Today's library seminar is titled Estimating Natural Mortality in Size-Structured Models. The presentation is part of the National Stock Assessment Science Seminar Series, which is developed by NOAA Fisheries and organized by Kristen Blackheart from the Office of Science and Technology. Today's speaker, Lee Cronin-Fine, will be introduced by Kristen. But before I hand over the mic, here are a few housekeeping items for our live audience members to improve the webinar experience. If you're having trouble with the audio or the visual components of GoToWebinar, I suggest that you log out and rejoin us. This will reset their software and usually resolves most technical issues. This presentation is being recorded and will be available on the NOAA Central Library YouTube channel later today. I will add the channel's link to the chat box. Our speaker has shared his slides, so please feel free to download them from the handouts menu in the webinar control panel. And last but not least, we are very interested in your questions and we encourage you to ask them throughout the seminar, even though the speaker will not address them until the end of his presentation. All audience members are muted, so type your questions or comments in the chat box under questions located in the webinar control panel. So with that last detail, let's get started. Kristen, the mic is yours.
Thank you, Lisa. As I mentioned in the announcement for this seminar, our theme of this year's seminar series is early career professionals, including students. And I am really excited to kick that off with Lee Cronin-Fine, who is a postdoc working with Megan Bryan. Lee attended Brown University and then moved on to Northeastern University, where he worked on alewife. After that, he worked as a fisheries observer in the Bering Sea, and then came to the University of Washington here in Seattle, working in the Punt Lab, and now is currently doing his postdoc work. So quite a bit of experience under his belt working on some pretty interesting and varied systems. Today he'll be talking about natural mortality. So with that, I'm just going to hand it over to Lee and give him the rest of the time. Thanks for being here today, Lee.
Thank you for inviting me. Welcome everyone to my talk. Thank you for attending. Today I will be talking about the last chapter of my dissertation. Now, in the world of stock assessment, a very important and key aspect, as I'm assuming most of you all know, is my slide, mortality. This is a very big driving force in all models and can definitely strongly impact results. Now, in most stock assessment models, mortality is usually divided into two parts. The first part is called fishing mortality, which is basically just the mortality caused by fishing. And the other part is natural mortality, which accounts for everything else. Natural mortality can have a lot of influence in stock assessment models, and it influences a variety of different aspects within the model. This includes things such as the spawning stock biomass, the maximum sustainable yield, and the fishing mortality rate, just to name a few. Now, natural mortality also can have a high degree of variation. Now, this variation in natural mortality can be caused by a variety of different things. This includes things such as sex. So basically this occurs when typically occurs when there's some degree of sexual dimorphism in the species. You can also have natural mortality vary by age. An idea out of this is that younger individuals or individuals that are mature have a higher mortality than older individuals or something like that. It can also vary by size, kind of having a similar idea that as maybe individuals get bigger, they're harder to catch and they're better to stay away from predators, so their natural mortality decreases. Another possible source of variation in natural mortality is time. So there are a lot of factors can cause natural mortality to vary over time. These things include such as changes in predator dynamics or changes in environmental conditions that make it either easier or harder to live. Now, Considering all the influence that natural mortality can have in stock assessment models and all the different ways it can vary, it would be great if this parameter was easy to estimate. Unfortunately, it is not. There are a variety of reasons why it is difficult to estimate natural mortality. Some of them include things such as the impact of fishing mortality. So it's actually fairly difficult to separate fishing mortality from natural mortality and try to distinguish the two since they're also closely related. Research has also shown that natural mortality can be correlated to a variety of different aspects within the model or within stock assessment models, including recruitment, selectivity, and growth. So considering the difficulty in estimating natural mortality, a lot of stock assessments decide to set it to a fixed value and not estimate it. However, a lot of research has shown that it's in general better to estimate natural mortality than it is to fix it. Now, this research has focused on age-structured models, which is a very popular form of stock assessment model that is used in a lot of species. Now, these models track the population by age. Unfortunately, there are a lot of valuable fish stocks out there that are difficult to age. These species typically include things like crabs, lobsters, and prawns. These species are difficult to age, typically because they have an exoskeleton that molts on an irregular basis, which means that there's nothing really on them that can be aged. So for these species, a good alternative stock assessment model is a size-structured model that tracks the population by size. Now, there are a variety of unique characteristics within the size-structured model that aren't in an age-structured model. Some examples of this include something called a size transition matrix, which you can see an example of on the right-hand side. Now, I'm not going to take the time to explain exactly how this size transition matrix works, but this is basically how the model tracks the population's growth over time and how the distribution of different sizes changes. Another aspect of size structure models that's unique is something called terminal molt. Now, as I stated earlier, the species that are hard to age usually have an exoskeleton that molts on an irregular basis. Now, some species have a situation in which when they transition from immature individuals to mature, they stop molting and therefore stop growing. Thus, it's called terminal molt because once they mature, they stay at that size. So with these unique characteristics that can occur in size structured models, it's possible that these unique characteristics could impact the estimation of natural mortality because, as I stated earlier, there's some evidence that there's some degree of correlation between growth and natural mortality. And as I stated earlier, most research on investigating natural mortality has focused on age-structured models. So this brings me to the questions I wanted to address in my last chapter of my dissertation. Now, the first one is a pretty straightforward question, but important, is can size-structured models estimate natural mortality, and can it do it well? Next one is what impacts the ability to estimate natural mortality in size-structured models? So by this question, I'm thinking about what assumptions within the model impact this ability. So if we assume growth is fixed, or if it's estimated, or things like, or if there is terminal molt or not terminal molt, did this impact our ability to estimate natural mortality? And the third question I wanted to address is how does estimating natural mortality impact the overall performance of size-structured models? So with this one, I'm basically there's a lot of desired outcome values from assessments that we are interested in. And if we estimate natural mortality, how does this impact these desired quantities that we're interested in, such as spawning stock biomass? So yes, so that brings me to, so these are the questions I want to address in my chapter. And I will do this by focusing on 3 different aspects within a stock assessment model. First, I'm going to look at how the assumptions behind natural mortality. I'm going to look at whether we assume that natural mortality is constant over time. So here's a figure of the natural mortality value over time. We have the value on the y-axis, time on the x-axis, and as you can see, it's fixed, or a single value is estimated for the entire time for the entire species. Also can consider the option in which natural mortality varies by sex and maturity stage. So that will involve 3 different parameters, one for mature males, one for mature females, and a third one for immature males and females. And the third way of modeling natural mortality is to assume that it is time varying. And I will assume that there is a linear increase in natural mortality over time. The second aspect I'll be looking at is the impact of growth on estimating natural mortality and overall model performance. And I'll be looking at whether or not having growth estimated or pre-specified impacts performance. And third, I'll be looking at the impact of terminal molt and looking at whether or not having terminal molt in your model impacts the performance and ability to estimate natural mortality. Now, with these 3 characteristics that I want to explore with the questions I was interested in, I will address this through a simulation study. Now, for my simulation study, my population will be modeled after the tanner crab population in the Bering Sea of Alaska. Now, any simulation study is divided into 2 parts. The first part is the operating model, which represents the real world. Now, unfortunately, there's a lot of different aspects of the world that we do not fully understand or don't know. So in simulation studies, it's fairly common to have multiple versions of the operating model, all with different assumptions about how the real world works. I'll then generate data from the operating model and apply them to estimation methods that are models that have different assumptions about how the real world works. And the goal is to try to determine which estimation method performs best. And I'll apply it to all the different operating model variants. So in my simulation study, I will have 3 different operating models, each with their own assumption for how natural mortality works. Take a minute, I need some water. All right, so I will get back. I'm talking about the 3 operating models. So they vary based on how natural mortality is modeled. The first assumes that natural mortality is constant over time, which is the middle one, or which I call the single operating model. The second assumes natural mortality varies by sex and stage, which will have 3 values for natural mortality, 1 for adult males, 1 for adult females, and 1 for immature males and females. And the third assumes time varying natural mortality, which will have a linear increase in natural mortality over time. I will then generate data from these operating models and apply them to 4 different estimation methods. The first will have natural mortality fixed to a set value, and it will be set to the same value as in the operating model, which is a little different based on which one we're looking at here, which operating model. The second is you're going to estimate a single value of natural mortality for the entire population for the entire time. The third will estimate 3 values of natural mortality based on sex and stage. And the fourth will allow for time varying natural mortality through a blocking design. Now, I'm going to take a minute to explain what blocking design is. And here we have an image that's kind of a visual representation of blocking design for allowing for time varying parameters. So on the y-axis is the value of your parameter. So for us, this is natural mortality. And on the x-axis is time. Now, the dotted line represents the initial value of natural mortality, and the dark colored long dashes represents time blocks. Now, within each time block, natural mortality is estimated to a single value, but between time blocks, natural mortality is allowed to vary. So basically, this allows for some degree of time varying natural mortality within your estimation model without having to estimate a new value of natural mortality for each year. So as you all might remember from some previous slides, one of the things I want to look at is the impact of having growth either estimated or pre-specified. So in order to do this, I will take my 4 estimation models and I'll apply them twice to each operating model. One in which growth is estimated, which is represented by the green color, and one in which growth is pre-specified, which is represented by the blue color. Now I will take these 8 different estimation methods and apply them to all of my operating models. Now, as you can see, when you look under the second stage operating model, there is no blocking design estimation method. And when you look under the time varying operating model, there is no section stage estimation method. The idea behind this is that the assumptions between estimate natural mortality varying by second stage versus having it being time varying are very different, and applying them to an operating model in which has differing assumptions is not a very straightforward thing to look at. So I decided to ignore those and just base it on the design I have here. Now, as I've stated before, one of the other things that I was looking at is the impact of terminal Molt. So I'll take this simulation study design and I'll apply it twice. Once in which there is no terminal Molt in either the operating model or the estimation method. And again, when there is terminal Molt in the operating model and the estimation method, and I can compare the two to see the impact of having terminal Molt. Now, there are multiple techniques I use to evaluate the performance of my estimation methods. Before this talk, I'm going to talk about two methods that I used. First, I looked at the ability to estimate natural mortality within each estimation method. And I did this using something called the medium absolute relative error, or MARE. Below, you can see the equation for the MARE, which is basically just the estimated value minus the true value, take the absolute value of it, divide it by the true value, get the median, times it by 100. The way you can read this value is the lower the MARE, the better performance or the better estimation you have of natural mortality. Oh, sorry, that's my alarm. Okay, sorry about that. Second is I will be looking at the relative error in spawning stock biomass. And I'll be using this to evaluate the relative performance of each estimation method to produce desired quantities. So now I will first begin by showing some results at the ability to estimate natural mortality. So I will show the results with figures that looks like this. Where on the y-axis, you have the MARE value for natural mortality, and on the x-axis, you have the estimation method. In this figure, the only estimation method shown is the one that assumes a single value of natural mortality is estimated. Now, in these figures going forward, when I show natural mortality, I do not show the fixed estimation method because the natural mortality is set to the true value. So the MARE will be 0 because it's set to the true value. So I just did not show it. Now this figure here, the color represents whether or not growth is estimated or pre-specified. So once again, green means growth is estimated and blue means growth is pre-specified. Now this is from the operating model that assumes a single value of natural mortality for the entire population. And this is also in the scenarios in which there is no terminal Molt. Now the takeaway you can get from this figure is that it appears that having growth pre-specified produces a better value of natural mortality than having growth estimated, since the MARE is lower for pre-specified growth versus growth estimated. Now let's look at the impact of having natural mortality vary by sex and stage in the estimation method. So this is an extension of the graph we saw before, where once again we still have the y-axis is the MARE for natural mortality and the x-axis is the estimation method. 3 new values have appeared, all from the estimation method by section stage, where SS stands for the section stage estimation method, and the parentheses represents which natural mortality value is estimated. So M stands for males, F stands for females, and I stands for immature males and females. Other than that, everything else is exactly the same as the figure before. Now, there's a couple takeaways from this figure that we can see. First is that we see a consistent trend of growth being pre-specified, producing better estimates for natural mortality than growth estimated, regardless of the estimation method. And we also see that when it comes that for the second stage estimation method, it has a lot of difficulty estimating immature natural mortality because those bars are significantly higher than the rest. Other than that, each estimation method did a pretty fair and good job at estimating natural mortality. Now let's look at the effect or impact of having natural mortality vary over time through the blocking method in the estimation method. So here, something I forgot to say earlier, but in the blocking design, the timeline for the fishing population is divided into time blocks. Now, in my estimation method, I divided the timeline into 10 time blocks, each time block having 5 years. So that's resulted in 10 time blocks. So on the x-axis, you see numbers 1 through 10, which represents the 10 different time blocks, where 1 is the earliest part of the year and 10 is the latest. Now, the takeaway you can take from this is there's a couple things you can see. First is that the trend in which growth being pre-specified results in better estimates of natural mortality seems to stay consistent with 2 exceptions with regards to time-varying natural mortality and estimation method. And also that all the estimation methods did a fairly good job of estimating natural mortality with some degree of variability in that performance. Now, I'm going to take this figure and look at what happens when there is terminal molt. Now, as you can see in this transition, there isn't that significant of a change except for the section stage estimation method estimation of immature natural mortality. But the overall general trends are still the same, in which pre-specified growth tends to produce better estimates of natural mortality, and all estimation methods did a fairly good job of estimating natural mortality. Now, to make this a little clearer, I'm going to transition between this slide and the previous so you can see the difference. Also keep in mind that the y-axis does not change between the two figures. So just to quickly show, I'll take it a little slow on this, but you can kind of see there is not that significant of a huge change in overall performance. So, some general observations we see through this first operating model scenario is that, as I've been saying, natural mortality seems to be better estimated when growth is pre-specified. There seems to be difficulty in estimating immature natural mortality, and there really isn't significant difference, or there seems to be very little difference between having terminal molt and not having terminal molt. Now let's see if this trend stay consistent when we change the operating model to one that allows natural mortality, that has natural mortality vary by sex and stage. So this is very similar to the graph we saw before. The only difference is the operating model is now assumes natural mortality varies by sex and stage. There is no terminal molt currently in either the operating model or estimation method. The y-axis is still the MARE value, and the x-axis is the estimation method. And the color is growth estimated is green, and blue is growth pre-specified. Now, there is no time-varying natural mortality in the estimation methods. As I stated earlier, they were not applied to this operating model. And the way these estimation methods are grouped is a little different. So what I did is I separated them out based on which natural mortality value is being estimated. So the first group estimates the male natural mortality parameter. The second estimates the female natural mortality parameter. And the third estimates immature natural mortality parameter. Now on the y-axis, SS still stands for the second stage estimation method. On the x-axis, SS stands for the second stage estimation method. But as you can see, there are 3 single estimation methods. This does not mean that I estimated 3 different single estimation methods. These 3 are the same estimate, all assume one value for natural mortality for all 3 different all 3 natural mortality parameters. It's just this is the comparison to the 3 different natural mortality parameters from the operating model. So that's why you see them different. All right, so conclusions we can see from this figure is that once again, there's a general trend that having growth pre-specified results in better estimates of natural mortality than having growth estimated. It's not a universal trend, but it's still on a more likely than not that does occur. And we do start seeing that when the estimation model that allows for variation in section stage performs better than the single estimation method, especially for the male and female natural mortality parameters. Now, if we take this graph and look at terminal molt, we again don't see that big of change in results. The general trend in relation to growth being pre-specified performing better stays the same, and overall performance stays the same as well. Also, another trend that I forgot to say before that's also still apparent here is that the second stage estimation method still has trouble estimating immature natural mortality. So I'm going to take a second and transition between the two so you can see just how little difference there is between having terminal molt and not having terminal molt. So once again, the general trends that were stated in the first operating model, in which there was a single value of natural mortality, have stayed pretty consistent when there is natural mortality varying by second stage. Pre-specified, having growth pre-specified produce better values of natural mortality. Immature natural mortality is still difficult to estimate, and there's little difference between terminal molt and no terminal molt. Now, finally, I'm going to look at the impact of having a time-varying natural mortality in the operating model. Now, once again, this figure is the same as the ones I saw before, but I'm just showing the results for the estimation method that has blocking design natural mortality. The reason why I don't show it for the estimation method with a single value estimated is there's not really a direct comparison that can be made when there's time-varying natural mortality for calculating the MARE. So as you can see here, the trends, once again, sorry for a second. Some weird noise in the background. Okay, back to what I was talking about. As you can see, the trends in which pre-specified growth produces better estimates of natural mortality than having growth estimated are once again pretty consistent as well, with a couple little exceptions to this. And I'm going to take this graph and then again look at the impact of terminal molt. And as you can see, the trend is also still the same, where you still see a general trend of growth being pre-specified, producing a better estimate of natural mortality. However, it's not universally consistent. There's about, I think, about 4 exceptions in this figure and 2 in the previous. And I'm going to transition between the two to kind of just show you there isn't that significantly of a change in performance. So what are some conclusions we can draw from this first part of the study looking at the estimation method's ability to estimate natural mortality? First, we seem to get this general trend that it's better to estimate natural mortality when growth is pre-specified. And I think what seems to be going on here is that you're kind of decoupling the correlation between growth and natural mortality when it's fixed. So natural mortality is allowed to be estimated better, and more of the data is being used to estimate natural mortality and doesn't have to deal with growth. So I think that's what's going on. And this trend seems to be consistent and does not vary depending on the operating model or the estimation method. Another thing that seems to be pretty consistent is that estimation methods seem to have trouble estimating immature natural mortality. This is predominantly true for the sex and stage estimation method. Now, what I think is going on here, it has to do with selectivity. Now, in my estimation method and in the Tanner-Crab stock assessment, there are 3 selectivity curves. I think there's 4 technically in the Tanner-Crab actual assessment, but I only use 3 because these are the ones that do the largest amount of catch. So the 3 curves are the directed catch, which is the directed catch, bycatch, and the survey. Now, if I superimpose the maturity curves onto this figure, you can start to see what might be going on. Now, when the selectivity curve is to the left of the maturity curves, that means that that fleet catches a good amount of immature individuals. But if the selectivity curve is to the right of the maturity curve, it means that those fleets do not catch immature or do not do a good job of catching immature individuals. And as you can see, the large amount of information or the majority of information for immature individuals solely comes from the survey. The bycatch and the directed fleet catch very little, if not any, immature individuals. So what might be going on here is that there is just not enough information on immature individuals to help to allow the model to estimate immature natural mortality. Now, the final conclusion is that terminal molt seems to have little impact on natural mortality estimation, which is a little surprising. I was expecting terminal molt to kind of reduce the correlation effect between natural mortality and growth and maybe decouple them a little bit, allowing it to be estimated better. But that trend didn't seem to be very consistent, nor to an extent that I would say is a overall good conclusion to that. So these are the 3 conclusions I have made based on just looking at natural mortality. Now let's see when we look at the estimation method's ability to estimate spawning stock biomass and see if these trends stay the same. So I will look at the ability to estimate spawning stock biomass with graphs that look like this. On the y-axis, we have the relative error in spawning stock biomass. On the x-axis, we have time. The title tells me whether or not growth is estimated or growth is pre-specified. So in this situation, growth is estimated. And on your right-hand side, that label tells me what estimation method is used. So in this example, it is the estimation method that has natural mortality fixed. Now the graph itself, here's how you read the graph itself. The red dotted line is just the 0 line. The white line is the median relative error in spawning stock biomass. The black shaded region is the 50% confidence interval for the relative error in spawning stock biomass. And the gray shaded region is the 95% confidence interval for the relative error in spawning stock biomass. Now the goal here is to have the white line on top of the red line and the black and shaded region tightly around the white line. The closer it is like that, the better performance you get. Now in this scenario here, I'm talking about, the operating model is the one in which there's a single value of natural mortality applied to the whole population, and there is no terminal molt. Now, when you look at this graph, you do get some information, but you can really start seeing trends when you compare it to other estimation methods. So here we have 2 graphs compared. The one on the left-hand side is the exact same one as before, and the one on the right, the only difference is growth is now pre-specified. All other characteristics are exactly the same. And as you can see, there is slight differences, but overall the performance is fairly similar between the 2, whether or not growth is estimated or pre-specified. Now, let's compare this with other estimation methods. So in this figure, we have the 4 different estimation methods. The operating model is still the same, and there's still no terminal molt. And so the top row, the 2 figures I showed in the 2 previous slides. The next row is the estimation method where a single value of natural mortality is estimated. The 3rd row is the estimation method where natural mortality varies by sex and stage. And the final row is the estimation method where natural mortality follows a blocking design. The left column is growth is estimated, and the right column is growth is pre-specified. Now, as you can see here, there is not much difference in performance. All estimation methods seem to do a fairly good job of estimating spawning stock biomass, and with little distinction between growth being estimated, growth being specified. Now, there does seem to be a little more variability in the blocking design, but it still does a fairly good job. And what I think is going on there is it's just the transitions of the different blocks. So if you actually count the peaks either at the top or bottom, there's about 10 of them, which I think correlates to the changing of each block. Now, if we take this figure and look at terminal molt, we can see that the trend is basically still the same, with very little difference between the 2. With all estimation methods doing well and with little difference in performance based on whether growth is estimated or pre-specified. Now we'll transition between the 2 figures to kind of show that the difference is very slight, but there isn't much of a difference. So once again, there are some observations from the first set of operating models is all estimation methods performed well. There's little difference between growth being estimated and growth being fixed. And there's also a little difference between having terminal molt and not having terminal molt. Now let's see if these trends stay consistent when we look at the next operating model in which natural mortality varies by sex and stage. So this is very similar to the graph we saw before. As I said, it's a different operating model. There is no terminal molt in either the operating model or estimation method. And I removed the row in which there is the blocking design estimation method because that was not applied to this operating model. Now, as you can see here, you do distinguish a difference between growth is estimated and growth being specified, specifically for the fixed and single estimation methods. Basically, growth estimated seems to be producing a better estimate for spawning stock biomass because it's closer to that red dotted line compared to being growth pre-specified. This predominantly occurs for the single and the fixed estimation methods. Now let's look at the same figure, but for when there is terminal molt. And as you can see, the trend is the same. We see a difference between growth estimated and growth being pre-specified, with growth estimated producing better results, and this predominantly occurring for growth being fixed and growth being a single value being estimated in the estimation model. Now I will transition between the two graphs as I've been saying, so you can see the difference between terminal molt and not terminal molt. So it's a little different, but once again, very little difference in performance. So now we have a difference in trend here going on, in which estimating spawning stock biomass seems to go better when growth is estimated. And again, we see that there's little difference between terminal molt and no terminal molt. Finally, let's look at what happens when the operating model has time-varying national mortality. Well, as you can see here, this is once again similar to what I showed before, but instead of having the second stage estimation method, it was replaced with the blocking design estimation method. And again, there is no terminal molt in either the operating model or estimation method. As you can see, all estimation methods do a pretty bad job at estimating spawning stock biomass, with the single and fixed estimation methods doing significantly worse than the blocking design estimation method. You also see that there is little distinction between growth being estimated and growth being pre-specified. So all estimation methods seem to have trouble with blocking design performing better, but still having difficulty compared to the single and fixed estimation methods. Now I'm going to take this graph and look what happens when there is terminal molt. And again, you see the same trend in which all estimation methods have difficulty, regardless of how growth is estimated or pre-specified. And again, blocking design performs the best out of all the estimation methods, but still not great. So what are some conclusions we can draw from these results for the estimation of spawning stock biomass? Well, first, as I stated earlier, that there seems to be a trend in which estimating growth seems to allow for better estimates of spawning stock biomass. And what I think is going on here is that by estimating growth, you're allowing the estimation methods to be more flexible. So, and I think this is apparent because you see this benefit of estimating growth when the operating model and estimation model do not match in their assumptions for natural mortality. So growth allows the model to be more flexible and thus give you a better estimate for spawning stock biomass. However, this does not seem to be a universal cure, because as you can see, when there is time-varying national mortality, or as I showed, when there is time-varying national mortality in the operating model, having growth estimated does not really fix anything. Another conclusion is that as I was stating, all estimation methods have trouble estimating time-varying national mortality. However, blocking design performs significantly better than the other two estimation methods of fixed or a single value, but it still has difficulty with it. And finally, terminal molt seems to have little impact. Well, that wording should have been fixed, but terminal molt has little impact on estimating spawning stock biomass. So once again, you see that whether or not there is terminal molt or there isn't terminal molt, the general performance of an estimation method stays the same. So now that we have this information, what recommendations would I give if you are going to be dealing with national mortality and size structure models? So first, I would say that in general, it's always better to estimate national mortality than fix it. There are some other runs I've done before that showed that when national mortality is set to the wrong value, things go significantly worse. And in the scenarios I showed here, national mortality is set to the true value, but even in those cases, you can have problems. Second is that when there is evidence for either time-varying national mortality or national mortality varying by sex and stage, it's probably better to include that in your estimation method. It's not the difference between having it, so that's probably a better way to do it. I would say if there's evidence for it, you should include it. And then finally, when it comes to growth, there seems to be a trade-off situation going on here. And it really depends on what you are interested or what your desired outcome in your model. So if you want a better estimate for natural mortality that's more representative of reality or more accurate, I would recommend probably estimating growth externally and then pre-specifying it in the estimation model. However, I will acknowledge with a little caveat is that in my work, when I pre-specified growth, I set it to the true value. So I do not know how robust this is if the growth parameters are slightly off. As for if you're more interested in the desired outcomes from the model, such as spawning stock biomass, I would estimate growth. However, the one thing that I feel like needs to be aware is that when you do this, you will most likely get better estimates for your spawning stock biomass. However, your parameter estimates have a good chance of being off and unrealistic or not what is truly occurring. So your natural mortality and growth will be slightly different than what is probably truly going on there, especially when the assumptions in your estimation model do not match reality. So with that, I would like to thank my funding sources for funding my last chapter of my dissertation. And if you have any questions, feel free to ask, and you can email me at the email below.
Thank you, Lee. That was wonderful. I really appreciate your presentation. So audience, this is a great time to ask your questions. We have about 15 minutes to do so. If you're interested in asking a question, just go ahead and write it or type it in the questions chat box, which is in the log on the right side, and I'll read them to Lee. And also as a reminder, Lee has provided his slides for us, so if you'd like to download them, they're also in the control panel under handouts. So please feel free to take care of that. And while we wait for questions, I also want to remind people that this is a recorded webinar. And if you know somebody who might be interested in Lee's work, please forward it to them. So Lee, we have a first question here. It says, thanks, Lee. Did you investigate the various data sources for their information contents regarding estimation of natural mortality?
Yes, so there are additional things I did in this chapter that are not included in my presentation. I did look at data source. Specifically, I looked at the amount of information in the size composition data and the amount of variability in the biomass index. And what I saw from there, which I do not have the slides for, unfortunately, right here, is that there was very little impact. It didn't really seem to impact the ability as I varied different aspects of those data sources. However, my conclusion from that is that my degree of variability might have been too small, or that there might have been other data sources that were more important. So I did, but there wasn't much evidence of a strong impact one way or the other.
Thank you. Let's give it another minute to see if any more questions come through. Meanwhile, did you have any final comments you wanted to make?
It was a pleasure. Thank you for letting me present. It was nice to go back to some old work from my dissertation.
Excellent, no problem. Thank you for being here. All right, it looks like that might be the last question. I always say that very slowly because, here's another one. And that's exactly why I say it slowly. This next question asks, how do you validate these results?
Okay. Let me think about that. When you mean validate, you mean applied to the real world? I feel like, what's my call? How do I validate these results? So
yes, this person says yes. That's exactly.
So the thing is with the I'm going to think about that for a second, because the goal of this right now is that obviously this is a simulation study, so I can control different dynamics towards it. And the one thing is that obviously I try to allow there to be variability in the operating models and the different scenarios. So it's a general characteristic based on the scenarios I'm looking at. So going further into reality, since we don't really know what natural mortality values are out there and things like that, it's going to be a little more difficult. What could be done is to go to the degree of validation is to try to compare estimates. For example, like one of my theories is that when you estimate growth and natural mortality at the same time, your parameter values might be off if the assumptions are wrong about your model. So you could check that with other studies that specifically just estimate natural mortality values or growth and see, are those values slightly different, or are they coming pretty close? And that could be a potential way, and especially if you have an assumption in the model that most likely does not match reality. That's one way to validate one of my possible suggestions from my research. But so that's one way to do it. And yeah, I guess the other thing is to look at and expand the degree of operating models you look at, to look at the degree of potential variability from reality and see if these trends stay the same.
Thank you. We did get another question. This question asks, how will the random effect estimation capabilities of TMB change how time varying M would be estimated here?
Yes. So you're talking about TMB and its new capability. So all the work I did here, the estimation method was done in ADMB. So I have done a little work with TMB, so I'm not as familiar with the differences in it. So I unfortunately I'm drawing a blank on that because I just don't know the full extent of the differences. I would be happy to take a look at that and see how it might have impacted, but I agree that I know TMB has more capabilities and it might change the overall outcome. Difference between the estimation method and operating model. I mean, between the estimation method being an ADMB versus TMB. So unfortunately, I can't answer that question better at the moment since I still am getting better at TMB at the moment.
No problem. I do send all the questions to Lee, so he can respond offline when there's a lot less of a spotlight on you. We did get another question. It says, do you explore any characteristics of the data or diagnostics that would indicate when natural mortality might be estimated accurately?
Okay. I'm not sure if you're applying to whatchamacallit, whether like actual data or my simulated data. So the accuracy of it, what I've done here is I showed results for the MARE, which is basically just a median value, but there are additional other figures that I looked at as well that kind of shows the degree of variability in these estimates. So I have box plots that kind of show that how variable these estimates are to it. Now, the overall result from what I remember is that there wasn't a large amount of variability, but it did differ depending on the estimation method. So yes, I did do that. I do not have the figure here, but this is once again is just for comparison within parameters generated from the operating model where I actually do know the true value. So I didn't do any work where I looked at actual data and tried to see what's going on there. So, but yeah, I have this paper. I should be publishing a paper on this soon that will go into more detail, or I'll be more than happy to share you figures that show the degree of accuracy of the natural mortality estimates from the operating model.
Excellent, thank you. Looks like that might be the last model. Oh, this person says, thanks, I did mean the simulated data.
Yeah.
Just to confirm.
Yeah.
Excellent. All right, so if there are no other questions, but maybe you have one that will sneak up in the next few minutes after we end the webinar, please feel free to email Lee. The email is lee.cronin-fine@noaa.gov. And thank you so much, Lee, for your presentation today. And Kristen, of course, for organizing the National Stock Assessment Science Seminar Series. I would like to also thank everyone for joining us for today's seminar. We hope that you'll join us again next month for a National Stock Assessment Science Seminar, which is always hosted on the first Thursday of the month at 3 p.m. Eastern Standard Time. So enjoy the rest of the day, and thank you so much, Lee.
Yeah, thank you for having me.
Absolutely.